Let's take a look at cubics. The perfect cube. A cubed plus 3a squared b plus 3ab squared plus b cubed. Now, I don't know if you've ever thought about it. In fact, I could even take this back to the quadratic. When you got a plus b squared, and you end up with a squared plus 2ab plus b squared, what are you actually doing? Well, what we're doing is we're getting a plus b and multiplying with a plus b. And we're taking one term out of each and multiplying them together. So therefore, all of our terms should contain two pronumerals. A squared, which is really a times a, it's got two pronumerals. 2ab, a times b, it's got two pronumerals. B squared, b times b, it's got two. Well, with a cubic, now what are we doing? We're going a plus b times a plus b times a plus b. So each term should have three pronumerals. So essentially, the pattern is all the possible combinations there of three pronumerals. So I have 3a, so a cubed. 2 a's and a b, a squared b. An a and two b's, ab squared, or I could have b cubed. That's where they all come from. And the pattern goes 1, 3, 3, 1. They're what we call the binomial coefficients. A minus b cubed, exactly the same pattern, but the signs alternate. Exactly the same as the perfect square. You might not have picked up on the alternating of the perfect square because you only got three terms, so you don't see the negative come back again. But in all of these expansions, we get that pattern. Plus, minus, plus, minus, plus, minus, plus, and you just keep going to the last term. So for the cube, you've got a cubed minus 3a squared b plus 3ab squared minus b cubed. We could generalise. Don't have to have just two terms in there. If we had a plus b plus c and keep going as many as you like cubed, we will get each individual one of them cubed. All of the ones where there's two of one pronumeral and one of the other, so a squared b, a squared c, ab squared. I mean, there's so many others I could have put down. I could have put down b squared c, c squared a, you know, all different ones, but there will be three of all those. But now we're going to have a possibility of just one of each of the pronumerals, A, B, C. There will be 6 of those. That's our generalisation of a cube. We have difference of two squares, we also have difference of two cubes. But now I can explain why it's more correct to put the minus first. Because the a cubed minus b cubed goes a minus b, and then in the next one it goes a squared plus ab plus b squared. Right? So you always start with the a minus b. The difference of two squares was a minus b, a plus b. Because what happens in the second parentheses is you then knock it down a power. So it was a cubed, we knock it down a power, a squared, and again, it has to be two pronumerals. So we go a squared, a times b, b squared. That's the pattern. But you'll notice the coefficients this time is always 1. That coefficient doesn't change. But interestingly here, with a cube, we also have the sum of two cubes. We don't have the sum of two squares. Not a nice, neat factorisation like that. But we do for cubes. And you'll notice the pattern is exactly the same. Another reason why we start with a minus b, because when it's a cubed plus b cubed, we start with a plus b, which is match. It was a cubed minus b cubed, so we match it. A minus b is what we start with. A cubed plus b cubed, so we match it. We start with a plus b. That pattern of knock it down a power, write down all the possibilities, going to the last one, b squared. But you'll notice here now, that's where the negative appears. But that alternating happens. Plus, minus, plus, and that's where we stop. Now, if I see 2a minus 5 cubed then, I go, right, we got a perfect cubed. Now, I probably wouldn't write this down, but this is what I'm saying. Well, that's the pattern. It's the first one cubed, then there'll be 3 lots of, okay, knock it down a power, 2a squared, but now the 5's to the power of 1. Then knock it down a power, 2a's to the power of 1, 5 is now squared. The powers always add up to be whatever the expansion is. In this case it's cubed, the 2 powers always add up to be 3. And we end up with 5 cubed, but in this one, because it's negative, those signs are alternating, plus, minus, plus, minus. That's probably what I'd write down straight away. But again, if you find yourself making silly little errors, which we all do, then put an extra line of working out in. Sum of 2 cubes. Well, that is x cubed plus 2 cubed. So it's x plus 2, match it. x cubed plus 2 cubed. Match it, x plus 2. Now, knock it down a power, x squared. The product, 4, but the negative now appears in the second one, so we've got minus 2x. Difference of 2 cubes. Well, that is y cubed minus 3a all cubed. Match it, y minus 3a. Knock it down a power, y squared. The product, 9a squared. In this case, they're all pluses in the second one because the minus is in the first one. Again, it's something where we probably just write the final line down on that. We're more thinking that, but if you find yourself making silly mistakes, put the extra line in. In fact, this generalises really nicely. A to the power of n minus b to the power of n. You match it, a minus b. And there it is. A then, knock it down a power and just keep going down until you're left with b to that power. So b to the n minus 1. If it's minus in the first one, all of them are plus. You'll notice I haven't boxed the a to the power of n plus b to the power of n. And that's because only odd numbers. It doesn't work for even numbers. Let me show you. Here's x to the power of 5 minus. Well, it's minus anyway. Nice simple one. Match it, x minus 1, knock it down a power. All the combinations, pull it through. And there's our factorisation. Okay, it's an odd number, because this is what we're really doing. Now, this is not how I would do it in reality, because what we're really doing is turning it into the form of the formula that we know. You see, if it's an odd power, I can always turn it into negative 1 to the power of something, but then put the negative out the front. That will still end up being plus 1, because negative 1 to an odd power will always be a negative number. And so negative becomes a positive. It works with odd numbers. It's not going to work with an even number, however, because negative 1 to an even power is a positive number, so I can't get that negative out the front. That's why we don't have one for the sum of 2 squares, the sum of 2 quartics and things like that. But now I can, because I'll match it. A minus minus 1 is a plus 1. But this is why we get the alternating pattern, because we're now saying negative 1 to the power. So in that second term there, that negative a to the 5, what I've really got is plus a to the power of 5 times negative 1 to the power of 1, which is negative. And so every second one where that power of negative 1 comes in is going to an odd number, and that's why the negative is coming through. Well, that's all I need to know. I don't need to know it's a to the power of 7 minus 1 to the power of 7. I just need to know, hey, essentially that pattern. Match it, a plus 1, and then in the second one, I just alternate, plus minus, plus minus, plus minus, until I get to the end. Now, our new textbook doesn't seem to have an exercise on this stuff, but I still think it's worth looking at. So in our handouts, there would be an exercise from the old Cambridge book, and there's a handful of questions from that one.